As you would have seen the earlier video, I had explained how you can get a dataset, clean it, and have it prepped for machine learning. If you want to go ahead and have a look at it again, I would leave a link over here in this video. But today, let's move ahead a little bit further and see how we can predict from the clean dataset that we just prepared, which is actually based on a passenger data that is freely available for us to use. So let's get started. To begin with, we import the usual number of libraries that we use. For example, the NumPy, Pandas, and we also have the sklearn model selection, ensemble, and then the metrics. I'll get to the details why we need the metrics part down below. So first, what are we going to do is we will be loading our dataset. So we have cleaned our dataset in our previous video, which you had seen. The same thing, wherever it is located, you just load it. And after that, what we would do is we go ahead and scale the numerical features. So why do we need to scale numerical features? Whenever you have some kind of data which is huge, like for instance, the passenger count in a dataset, it will not converge faster. The machine learning algorithm, whatever we are using, it will take time to converge, and even if it takes that much amount of time to converge, there will be a lot of errors, meaning like it will not fit your algorithm properly and it will fail to detect patterns. So what we are trying to do is we are trying to use the standard scaler library that is available from sklearn preprocessing, and we just scalar.fit transform. We use this and it does that on that column. So we just replace the existing column with this scaled value. And as you can see, after you have scaled it, you would see the head. I'm just seeing the 5 rows from the dataset. And as you see here, the passenger count is reduced from what it was like hundreds of thousands of passengers to just the scaled value. Good. Now what do? We go ahead to split the dataset, right? And before we even split, we need to get the x and y value out of it. So the y, we should call it as y values, like it's a set of the target variable, and the y value has the target variable and the x contains the features which we model on, right? So we give it as a passenger count, we drop it, and once we drop this, we will get the remaining other columns, and the y we just assign one of the columns, the target variable. Going down below, as I had mentioned, we'll split the data into train, test, and we use the test size as 20%, 0.2, and we use our random seed as 42. Going down, we create the model or define the model, right? We use the GradientBoostingRegressor. So for our specific use case, we are going ahead with the gradient descent algorithm in the GradientBoostingRegressor. So this is something which I saw is much more suitable for it, and probably in another video I'll say how to choose a model for your dataset, so that it's much more in-depth, and I don't want to pack too many things into just this video. So let's go ahead with the GradientBoostingRegressor. And for this exact model or this type of model, there are certain hyperparameters. So we have the basic 4, the learning rate, subsample, n estimators, and max depth. So the learning rate actually controls how you can get more accurate convergence, right? So if you give it more like a much lower value, it will give you potentially like accurate convergence rather than compared to what you would get out of a higher value. Then subsample is the number of samples that you want to take from each of the tree in your training, right? And going ahead, we have n estimators. So the number of trees in your ensemble. So you have a forest, or you can say an ensemble which would would be used for for regressing or for getting the prediction. So if you give it a much lower value, it will result in a poorer performance. And like in our case, it is a little bit complex, and let's see how it chooses. So we'll be searching for it, but at the moment what we know is the lower value that you pass to an estimator will not work that much well for complex data sets. And going ahead, something we have called as a max depth. So the number of, or we can say it like the maximum depth each tree in your ensemble can go towards to get the prediction or to train on, right? So you can give you have like n number of values to choose from. Usually people choose something in the single or 2-digit range, and if in my case I am comfortable with choosing something like even values like 4, 6, 8. 2 I don't see that much of a good important value, so anything above 2 will be much easier to choose, or it fits better. So I give the values like 4, 6, 8, 10. So what it says is like it controls the complexity of individual trees. So if you want it to be more and more complex, it will be able to capture the more complex relationship in your data. So if your data is complicated and it has multiple features which depend on each other and has much more complicated relationship, it will be better to choose a higher value. But we will do one way, in a way that will help us to choose the best value, or something which I can call it as an optimum value for each of the parameters. So going down, we see that we have this set of value. We create this dictionary and we pass in these parameters, right? So we have the grid search CV, and as you had seen earlier, this is also one of the libraries available from sklearn model selection, and the same we are using here. And we pass in our model, we pass in our parameters which we want to search in, and we say cross validation as 2. So there is something called as cross validation, which helps us to provide a much better optimized fit for the data and also the model that we are using. So here we give the fold as 2, so that we get a much better fit. And the number of jobs here represent -1, right? And usually if you pass -1, it will use whatever whatever the number of cores available in your machine for the machine learning algorithms disposal. So you can say 2, 4, or 8. If you're not, the number of cores are 8, you can go with those numbers. Or if you just directly want to say, hey, use whatever core I have handy in my machine and use it for the prediction. So I gave it as 1, so that it uses all the cores available, and it does that in a very short span of time. If I give it like a number of cores as 1 or 2, it will take a little bit longer to do. And if you are running other things in your on your machine, it will be better to go in that route. But in my case, I just want to focus on my machine learning, so I gave it as -1. Moving ahead, we just fit it on the training values, xtrain and ytrain, and you give it a run. So as it runs, I've run it earlier in advance so that we don't take that time over here while we are explaining. So as you can see, it had ran it and it had produced the output, and it's very visual. You can see it visually, like it says all those that it went through, and it shows the tree view of it, and you can go through it and you can see what it did in a high level view. And finally, I gave something to print out what the search results from the grid search was. And as you can see, it said that the learning rate was optimized. The optimum learning rate that it found was 0.03, and the maximum depth it went and used to find the best value was 6, and the number of estimators it chose to be 1500. It went towards the higher end. That's good. And the sampling rate, it took the highest, so that's also good. Okay, what was the score? As you can see, it's 0.91, not bad. usually there is a saying like when you have a very high score, sometimes it might overfit, but you can tune it. So you can see like which is the best of both the worlds. Like you want the most accuracy and you want it to not overfit or underfit. So in our case, it shows these parameters, the whatever the tune parameters were, and it gave the score as 0.91, 91%. That's not bad. And we took those, right? And we took those and passed in as the best parameters. So if you pass it as the model dot best params, you can assign it to a variable and just pass it into the parameter for this gradient boosting regressor. And as you see down below, we fit for the model with the X train and Y train. And once you fit it, it completes. After it completes, we need to put this to test. Okay, let's predict the value for the X test. So we do the prediction, and once it does the prediction, we would have the values, right? It will do the prediction. And here I have the explanation for various metrics. As I had shown above, we have like 3 metrics which we are using: the mean squared error, R2 score, and also this one. Where is it? Over here. Down below you see mean squared error, RMS, root mean squared error, and R squared. So as you can see, each one of these help us to see how much we are off from the prediction. So the mean square error says like these number of units you are off from the actual values. So the predicted targeted value is this many units off. So in our case, the MSE is around 0.07, not bad. And the root mean square error is 0.28, which is just the square value. And the R2 score tells how much of a variability your model is explaining. So if it is like 0.75, it is like 75% it can explain the variance. In our case, it was 0.91, right? So it can explain around 91% or around close to 91.9, which is 92% of the variance in our dataset. So that's good. It's not that bad compared to what we are expecting. Finally, okay, we built our dataset, we trained it, we saw the errors, and we saw how much it is fitting and how well it performs. So now it's time to put the rubber to the road. We are trying to test the model for the dictionary that we have. So in our earlier case, we had actually built the data, and if you had seen in the previous video, we had the values for the number 1 record in our dataset. I could have chosen anyone. I just wanted to see how much of a closeness it is, how close it predicts to the actual value that we saw in the dataset. So we are trying to look for something closer to this value, and I built out the related fields or features with the proper values. So it is not arrival, it's departure, and it's on the 10th day of the 5th month in the year 2021, and it's of course it's AM PM. We give that encoded value, and the terminal is T1, which is shown by 2, and it is a domestic terminal as seen in this data, right? And we pass in the values, and now it's time for us to look for the actual value predicted. Once we run it, it gives the predicted, which is a scaled value based on the input scale data. So it gives us the value as 0.02, some value which is scaled. Now we need to reverse transform it. So, or in other way, inverse transform. So we use the same scaler which we used to scale our data, as you can see over here in the top. One thing to note over here is, if you use any other scaler or any other new scaler, it won't fit and it'll throw a lot of errors. Just make sure to use the same scaler that you used earlier to scale your input data. So you use this inverse transfer function and you use the reshape to shape it in a form that it can read, And as you can see, the predicted value is much closer. It's 150,000, right? And closer to 150,000, and the actual value is 160,000. Not bad. It's, as we had seen, it's 90, more than 90% uh, close to the value that we would see in a daily data or in the actual data. So this is how you usually do your machine learning through the gradient boosting regressor, and this is how you scale the data for your usage and then prepare your training and test data set, define and then tune your hyperparameters, search for the best parameters in your tuned value, and finally pass it to the actual model, fit the model and see the prediction, and finally check the predicted value or get the predicted value for whatever random data that you want to look for, and scale it back again to see the actual value, because this scaled value will not make sense in real life. You want to know what exactly the actual value is wherever you're using. So in our case, this value might be used in probably an airport terminal to make sure that you assign the number of places for the, or slots for each one of the planes to go in, or if you want to assign the flow of passengers or divert the flow of passengers, there you can choose, there you can use such kind of data which was predicted by a machine learning algorithm. So we can, this will be much more useful in day-to-day life, and probably this is not the best model. There may be some issues in my way of creating this model, but we can tune it further and we can play around with it to make sure that it fits properly to the use case that we are looking for. Thank you so much for joining the video and having a look at my video. Let me know your feedback if something needs to be improved, and let me know your comments. Like, share and subscribe. Thank you so much.